So when I talk about cyclic alkanes or cyclic alkanes, I'm talking about these carbon, hydrogen, single bond structures, but that are now in a ring shape, okay? And so we have hinted at these, but we haven't specifically talked about them. Okay, so first we're going to talk about just kind of the general energetics of these cyclic structures, and then we're going to move into figuring out, for specifically cyclohexane, what is the best conformation that it can be in as well, okay? So now, if we're thinking about tetrahedral carbon, right, so tetrahedral carbon is sp3 hybridized. What type of bond angles do we look at with respect to tetrahedral carbon? What is the idealized bond angle here?
No,
it's tetrahedral, right? So what is this bond angle, tetrahedral?
Oh, it's like 108.
109.5, right? So perfect idealized tetrahedron has an ideal bond angle of 109.5, okay? Now, as we start to think about these cyclic structures, especially with the way that we draw them right now, we're going to see that the less carbons there are, the more condensed this bond angle is, right? So for example, if we had a 3-member carbon ring, that would form, in theory, a triangle, right? What would these bond angles all be? About 60 degrees, right? Ideally, they want 109.5. So how energetically stable do you think this is going to be if they are forced to condense themselves to 60 degrees? Not very stable, right? So really early studies of all of these cyclic structures found that the most common cyclic alkanes were 5-membered rings and 6-membered rings. So this is a 5-membered and this is a 6-membered. We have cyclopentane and cyclohexane correspondingly, okay? And again, if we're drawing these in this perfect idealized bond situation, where these are all 2-dimensional, the bond angle for cyclopentane would be 108. The bond angle for cyclohexane would be 120. Who do you think would be more stable and found more often if we wanted to try to achieve that 109.5 bond angle?
The 108.
The 108, right? So original studies of this said, okay, well, nothing below this really forms, nothing above this really forms. These are the 2 main ones. And cyclopentane, because it's going to be idealized as close to that 109.5 bond angle, is going to be more energetically stable. Now, what's the problem with the way that this person was drawing these at the time? They're 2-dimensional, right? So that's the big problem with all of these. So, you know, we're thinking, oh, look at this, perfect 108, but in reality, this is not a 2-dimensional structure like we have drawn it here. It's a 3-dimensional structure. And we're going to find that as we move up, more things are going to form because, again, they can take on a 3-dimensional shape, okay? So, problem with the original studies was that they were drawing them in 2 dimensions. Instead, these are 3-dimensional structures. And so now we can kind of look at the ability of these various cyclic alkanes and determine who really is the most stable, okay? Okay, so there's a couple things to note here. For cyclopropane, we're looking at, with respect to stability, we're looking and going back to these combustion reactions. So for all of these, the way they're determining these heats of combustion is they're taking their cyclic alkane, right? So they're taking our cyclic alkane and they're reacting it with oxygen, forming CO2 and water, right? And they're measuring the overall heat of combustion for this reaction. This is the exact same thing that we did with our alkanes to determine, oh, well, the more branched an alkane is, the more stable it is. So it's the exact same concept here, okay? Now, also note that they're normalizing this per CH2 group because what happens as we increase the number of carbons here? We're not going to get the exact same products overall, right? So to kind of normalize for that, we're going to divide whatever this heat of reaction is by how many carbon groups are actually in there, okay? So that's going to give us this overall estimate of how stable each molecule is. So we look at these, there's not a lot of difference here, but who has the largest heat of combustion per CH2 group? Cyclopropane, right? So cyclopropane, because this is the largest heat of combustion, is the least stable of all of our little cyclic alkanes, okay? So as we go from cyclopropane to cyclobutane, we see a decrease, but it's still fairly high until we get to cyclopentane. And this is when we get into the 650 range. And we kind of stay in that range as we increase the number of carbons, okay? So these guys, we'll talk about why they're so high comparatively, but after we reach 5 carbons and we continue on, we're going to see a nice stabilizing trend. Still, in this, we can get a little bit more information out of this. So we have cyclopentane here at 658. We've got cyclohexane at 653. Who's the most stable between the two? Cyclohexane. Okay, so again, this goes against what von Baer actually originally postulated with respect to this. It's actually cyclohexane, which is the most stable of all of our ring structures. So this guy is more stable than anyone, and we're going to go through the reasons why that is in the next couple of slides, okay? Okay, so least stable is cyclopropane, most stable is cyclohexane, but again, once we reach that 5 carbon cutoff, we tend to reach this nice little plateau of stability, okay? Now, first one that we're going to talk about is the least stable of all of these guys, which is cyclopropane. We're going to talk about why we see such instability. Okay, so cyclopropane, when we talk about this instability, contains a significant amount of what is called ring strain. So there are 2 different components to this ring strain, okay? There's going to be an angle strain component as well as a torsional strain. So for example, let's say I take my little model kit here, and I take 3 carbons, so I've got 1, 2, 3, and I try to make another bond. See how difficult this is? I kind of have to bend my ring-like structure, okay, to get this nice little cyclic ring. This is what we mean by angle strain. There are 2 components to this, right? Number 1, these bonds, what's in these bonds? What in bonds specifically? Electrons, right? As we bring these electrons closer together and we get this 60-degree bond angle, we're going to get a lot of steric hindrance because of that, because this electron cloud is bumping up against this electron cloud. Number 2, this sigma bond, right? When we form sigma bonds, we need that orbital overlap. How well is this overlapping as it's doing this? We'd love to get this nice, beautiful head-on, but because this guy is so bent, we don't get this really efficient orbital overlap, okay? So that's 2 different reasons or 2 different things that contribute to angle strain. Now, there's another component to this, and that's torsional strain. So what is torsional strain related to? We talked about last time we had these different conformations. We had eclipsed and we had staggered, right? And the eclipsed was, right. So the eclipsed was so bad because all of those groups had that torsional strain. All of those groups were eclipsing, right? And we talked about the reasons for that. If we go around our cyclopropane structure here and we look at the Newman projection, the problem with cyclopropane is everyone is in the eclipsed position, right? So because of this is extremely unstable, because all of this torsional strain, because of everyone in the eclipsed position. So that's also what contributes to the ring strain of this. It's not just the angle strain, it's also the fact that all of these carbons are eclipsed. Okay, so 2 different things that we're always looking at with ring strain. Angle strain, which again goes back to that non-ideal bond angle, and then the torsional strain due to all of the eclipsing interactions from the various carbons in the ring. Okay, now if we break this guy up, and we add in, I've already bent my poor little bonds, they're never going to go back to normal, and we add in another carbon, right? So that was cyclopropane, the most unstable. With cyclobutane, which is going to be our 4 carbon group, we're going to try to again make this bond. It's going to be a little bit easier, right? So that's good. So we don't have as much angle strain for cyclobutane, but we still get significant amounts of torsional strain. Okay, so for cyclobutane, again, ideally we want this to be a 109.5 bond angle. Compared to cyclopropane, it has moved from 60 to now 80 degrees. So these guys are almost 90 degrees. There's still angle strain there, but most importantly, there's still significant torsional strain. So if we look at all of the carbons down their Newman projection, these are all still in their eclipsed interactions, okay? So again, cyclobutane has significant ring strain again. So ring strain that's coming from the angle strain, which is a little bit less than cyclopropane, but there is still significant amounts of torsional strain due to that eclipsing interaction. And this guy will actually take on what is called a puckered conformation. We're going to talk about, so if this was perfectly flat and 2-dimensional, you wouldn't see this, but when it puckers, these guys can bend up. They do kind of move slightly out of that torsional arrangement. So it does slightly pucker, which helps alleviate some of that torsional strain. Okay, so then if that's cyclobutane, who's next? Pentane, right? So now we'll add in one more carbon, and we'll add in another carbon. So now we have 5 carbons. We try to make a bond here. It's much easier, okay? So now we're getting to that idealized 109.5. There's not a significant amount of angle strain, but now there is still some torsional strain, okay? So if we look at this nice little picture of our cyclopentane, and notice again that we're going to see these bonds slightly pucker. What we get is eclipsing interactions between this carbon and this carbon, right? So these guys, if I draw around, are all staggered. This is a staggered, this is a staggered, and this is a staggered, which is good. That alleviates torsional strain, but we still get an eclipsing interaction here. Eclipsing interaction, which is still going to lead to that non-ideal torsional strain. Okay, and we can't get rid of that eclipsing interaction in cyclopentane. So again, the angle strain is now significantly decreased comparatively to butane and propane, and we still have a slight amount of torsional strain from the eclipsing interaction. Okay, so now that's cyclopentane. So in theory, that should have been the best one. It wasn't. Instead, the most stable molecule ends up being cyclohexane. Okay, so cyclohexane is our perfect, idealized, most stable of our cyclic ring structures. Now, there's again a couple of reasons for this. So cyclohexane has no ring strain. There's 0 ring strain in the most stable conformation. This is because all of these bond angles are a perfect 109.5, so there's no angle strain whatsoever. Most importantly, in the conformation where it is the most stable, which is what we call the chair conformation, there are 0 eclipsing interactions. So if you draw this in the chair, you can go around and look at all the bonds and find everyone is in the staggered conformation, okay? So now, why a chair? I know it's hard to see this, but notice, what does this look like? If we follow just the backbone of carbon, it looks like a lounge chair, right? And so that's why they call it a chair conformation, okay? This is the most stable conformation of cyclohexane, okay? Again, why is it stable? Well, there is no angle strain and there is absolutely no torsional strain. All of the carbons are in the staggered conformation. It's also really important at this point in time to be able to visualize the Newman projection of cyclohexane, right? So let's imagine that we are looking down this bond axis here, and let's say that we're going to call this carbon 1, 2, 3, 4, 5, 6. If we draw the Newman projection looking down these bond axes, our front carbon over here is right here, right? Our front carbon over here is right here, and our back carbon for this guy is 6, whereas this guy is carbon 4. This thing in the middle is carbon 5, and this thing up front is carbon 2. So this was 1, 2, 3, 4, 5, 6. And again, all of those are in the staggered conformation. Okay, so that's the most stable conformation for cyclohexane, but there is another conformation that it can interconvert to that we focus on as well, right? So again, all of these bonds can rotate, right? That's the entire purpose of this. So if we take this from the chair and we flip this bond up, it enters what is called the boat conformation, right? So why is it boat? Well, to me, it kind of looks like a boat, right? So this is our boat. Now, this is not as stable. The chair is more stable. This is the higher energy conformation. So this is higher energy. Now, why is it higher energy? We still have no ring strength. So these are still perfect 109.5 degree bond angles. But now, if we look at our conformations, most of these carbons, so these guys, let's say these guys, and these guys, and these guys, and these guys are all staggered, which again is energetically good, energetically stable. It's these two carbons here and these two carbons here that have moved into an eclipsing conformation. So these guys are eclipsing one another, which is introducing torsional strain. So this is why the boat is higher energy. Where did my boat go? Boat. This is why the boat is higher energy, because we do have these two sets of eclipsing conformations, which leads to torsional strain. Okay, so again, lowest energy is chair. All right, so chair, we can find it again, is here. Okay. At room temperature, though, depending on the groups that are on our little cyclohexane ring, we're going to be able to see conformational changes between our chair into what's called the half boat, into the boat, and then into the other half boat, into the other chair. So there are two energetically stable versions of this, one chair and the other, and they can rapidly flip back and forth between the two at room temperature. And they do, and that's going to be a big important point, okay? So notice when I'm doing this, I call this a ring flip, right? So I take my ring, we rotate into the chair, and then we rotate, the boat, and then we rotate into the opposite chair. This is what I refer to as a ring flip. This is not just flipping the ring. That doesn't work, right? When we're flipping the ring, we are taking one ring conformation, one chair conformation, converting it to the other chair by rotating bonds. Okay, so this, going through all of these various energetic conformations, is what is called a ring flip. Again, it's not just taking the ring and flipping it over, it's actually rotating these bonds, moving it through its higher energy conformations into its opposite chair. Yes?
And all that energy is hot temperature?
Yes. Yes, most of these, especially for a non-substituted cycloalkane, cyclohexane like this, would be able to do this at room temperature. Okay, so then one other thing that I didn't mention, there is another reason why the boat is energetically unfavorable, right? So if we go back up into the boat, notice that if we had groups here that are at the top of this boat, so if we had, let's say, a methyl group here, and then another methyl group up here, and we're in this boat conformation, what's happening between these groups? They're repulsing each other, right? So we've got a lot of steric interaction here, steric interaction here. This is what we call flagpole interactions, and it's another reason why the boat is energetically unfavorable, it's energetically unstable, because of this steric interaction in the flagpole position. So one other reason is our flagpole interaction in the boat. And again, that's just going to be due to steric interaction. Yes?
What is a twist boat?
A twist boat is kind of like, so it moves from, pop these off. So we're happy, we're super stable, and one chair, as we move in to the boat, right, we go through a really high intermediate half chair, and then whenever it's here, it finds a nice little kind of stable thing in the twist boat before it moves into the fully boat position.
Okay.
So these are all of just different transition states along this progression from chair to opposite chair. So it goes through a lot of different states in going from one chair to the other. Okay, so we're going to spend a lot of time with cyclohexane because, again, it is the most stable of our cyclic alkanes. But before we can really do that, we need to be able to draw the correct structure of these chairs, right? So what we've been drawing thus far are just a nice two-dimensional hexagonal structure. We're now going to learn how to actually draw these chair conformations. So I'm going to go through this. There's some key little bits and pieces I want to mention, and then I'm going to let you guys draw a couple of these on your own. So I always preferentially draw what I'm going to call the right-handed chair, and I think most people draw the right-handed chair first. But again, there are two versions of this, and we're going to go over how to draw both of them. So if we are going to draw what I call the right-handed chair, the first thing that we're going to do is we're going to draw a shallow V. Okay, so what does shallow V mean? So a shallow V is not this. That is not a shallow V. That is a very narrow V. Okay, so we don't like that. That's not what we're going to start with. Instead, we're going to draw a very shallow V-ish. Big fat V. Wide. Very hungry V. That's step number one. That's our shallow V. Okay, so now step number two, what we're going to do is we're going to draw a little dot, dot, dot line down the middle of our V. And we're going to go from the right-hand side, that's why I call this the right chair. And we're going to draw a line that's about 60 degrees from that down, that's going to end right before that dotted line. So we have our shallow V. We draw our nice line at 60 degrees down and stops right before the little dotted line that we've drawn. Next, we're going to draw another dotted line. We're going to go over to the end, to the left-hand side of our V, and we're going to draw a dot, 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 directly down. We are then going to start here where we ended, and we're going to draw a line that's parallel to this guy, and it's going to end right before that dot, dot, dot line. That may be a little too much. We're going to go with it. I hate drawing chairs anyways, so. Okay, so now, once we're here, we're going to draw another dot, 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 but it's going to be down here, dot, 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 that kind of ends where this guy has gone down to. And what we're going to do is we're going to start at this left-hand side, this guy, and we're going to draw a line down that's parallel with this guy over here. So this is going to go down, and it's going to end where that dot, dot, dot ends. Then finally, we're going to connect the dots, right? So we have this guy, it needs to be connected with this guy. We're going to do that with a line that is parallel to this guy. So we connect that, we have ended up with our chair shape. So what we end up with here are three sets of parallel lines. We've got our red parallel lines, parallel to one another, our black parallel lines, and our blue parallel lines. And again, this is what I refer to as the right chair because this position is pointing up. The rightmost carbon is the position pointing up when I draw this. Okay, so I'm going to do it one more time, and then I'll let you guys do some on your own. Okay, so first step. What is the first step? Shallow V, right? So we get a nice shallow V. That's where we're going to start. Second step, we're going to start on the right-hand side, draw a line down that's going to end before that dot, dot, dot. We've got another dot, dot, dot. Over on the left, we're going to draw a line going up parallel to this guy. So I'm going to move it into red. We're going to be parallel here. And it's going to end before the dot, dot, dot. We're then going to dot, dot, dot below. We're going to draw a line starting on the left-hand carbon up top, going down to the dot, dot, dot. That's parallel to this guy. And then finally, we're going to connect the dots. And again, that final line is going to be parallel to this line over here. That was part of our shallow V. Okay, so with that, I want to get you guys practice. So you will be turning these in, so I would keep hold of them, maybe write them on a separate sheet of paper. But I want you to practice drawing 3 of those cyclohexane chairs.
So when I originally had recorded this, I did have the students turn this in, but if you guys want to practice this on your own, you're not going to necessarily be able to turn this in. It is important to get practice in this, though, so I would draw them, and then, you know, I don't know, just look at them, see if they look like with the chairs that I've been drawing, etc. Again, another big helpful hint is the shallow V part. If you make a really narrow V, it does not work out very well. So make sure your shallow V, or what I've been calling a shallow V, is nice, it's open, it's got a big wide mouth to it, and that helps out in drawing these quite a bit.
The substituents. So right now what we have is we have our chair and we just have the carbon backbone. So now we're going to talk about these various substituents that we're going to have to add on to our chair position, okay? So again, if we start out with our chair, so this is a nice perfect chair that someone has drawn for us, which is nice. There are two different positions depending on where we're looking, okay? So if we go around our nice little right-hand chair, notice that we always have a position that points up and then something that points out, okay? A position that points down and something that points out. So these guys, which are pointing up and down as we go along the chair, these are called our axial positions. Whereas these guys in blue, these are called our equatorial positions. Equatorial positions, okay? So axial because essentially they point along an axis. Equatorial because they kind of center towards the equator of our cyclohexane ring. Okay, so we're going to have to add these on as well to our various cyclohexane rings that we have drawn. So the easiest position to draw in this is the axial position, because what happens with respect to the axial? They go up and they come down, and they go up and they come down, and they go up and they come down as we move along the ring. So that's going to be the easiest one to add on. All we have to do is draw an up and a down and an up and a down and an up and a down to add on those axial positions, pardon me. Now, the equatorial tend to be a little bit harder. So to illustrate this, I'm going to redraw a cyclohexane ring. So again, I'm going to start with my shallow V. I'm going to come down at about 60 degrees. I'm going to come across, I'm going to come down, and I'm going to connect my dots. So this is not ideal, not perfect, but we're gonna move on with it because we need to learn about these equatorial positions. So now, again, I have three sets of parallel lines. I've got red and red, I've got blue and I've got blue, and I've got black and black, okay? Now, we're gonna focus on the equatorial positions and learning how to draw the equatorial positions at each of these various carbons. And the first one we're gonna focus on is this carbon 1, okay? So now, at carbon 1, what we're going to find is that the equatorial position here is going to be parallel, not to the bonds that it's directly connected to, but to the bonds that are adjacent to it. So at that position, we're going to draw a parallel line that's parallel with the black, okay? So if we draw our black and our black, we're going to draw a parallel line to draw the equatorial position right there. So I'm going to go ahead and draw in all the axial because those, again, are easy. So 1, 2, up, down, down. I've drawn my first equatorial, that's black. So now I'm going to move to the next carbon, which is this guy. And again, I'm going to draw a line that's not parallel to the bond that it's directly connected to, but it's parallel to the next one over. So what color would that be on our little parallel lines? If I'm here and I'm wanting to draw the equatorial position, it's not going to be parallel to this or to this, but who is it going to be parallel to? The blue, okay? So when we come over here, I've got blue, I'm going to draw a line that's parallel to the blue. Okay? So if that's carbon 2, if we move on over to carbon 3, same exact thing. This equatorial position is not going to be adjacent or parallel to this or this, but who is it going to be parallel to? If we're here and we can't be parallel to black or blue, who are we going to be parallel to? Red, okay? So this guy is going to be parallel to red. We've got red, we've got red, we've got red. So then we move over to the next carbon, right? So next carbon, who is this going to be parallel to? Not the colors directly attached to it, but black. So again, we come over, we draw a parallel line to black. Next carbon, who is it going to be parallel to? Blue. So again, I always like to draw them, and then draw it so I can kind of keep that parallelness. And then finally, we get to the last little guy down here. Who is this going to be parallel to? Red. Right, so that's our red. So again, at each carbon, there are two separate substituents. There is the axial position, which for every of these guys, all you had to do is go, start up here going up, down, up, down, up, down along the ring. It's the equatorial, which become a little bit more of a hassle to actually draw on these. So again, each equatorial position is not going to be parallel to the ones that it's attached to. It's going to be parallel to the next one over. Yes?
So if the angle is pointing down, it'll go straight down?
It literally is going straight down.
Okay.
So if we're here, these guys literally go straight down. These guys literally go straight up.
Okay.
This guy is parallel to this guy. Okay, so let's try that. So now what I want you to do with your original cyclohexane ring is I want you to add on the axial and equatorial positions on all three of them. Yeah, what you already have, so you have the backbone already. Now I want you to draw on those axial and equatorial for each of them.
Yeah, so again, I would go ahead and go through this and get practice at drawing. The axial positions are nice and fairly easy. It's just up, down, but it's equatorial that kind of will give you a little bit of a hassle. And again, what I like to do is I like to just, like, if I'm making a line that's parallel to something else, I like to kind of mark over the line that I'm making it parallel to. It kind of gives my fingers or hands like muscle memory, and then I'll go ahead and draw the line. So I'll mark over the line I'm trying to make it parallel to, and then I'll draw the line that I'm actually making for my equatorial position.
To what happens when we add a substituent on, okay? So a substituent is going to be something other than hydrogen. So let's imagine that we do have a substituent, because I don't have any colored balls right now, and the substituent is, let's not draw that in red, the substituent is a methyl group, all right, so a CH3, because I do have a methyl group, okay? All right, so we have drawn this ring, which is great, okay? And so when I put my methyl group on this ring, it's going to go in the axial position, okay? So remember, this is one version of the chair, right? But isn't there another version of the chair as well? And can't we access it at room temperature? Yes, right? So when we undergo our ring flip, again, just via bond rotation and not just flipping this over, we rotate, where does that methyl group go? What position is it in now? So we're here. This is our first version of the chair with our methyl group in the axial position pointing directly up. This is our equatorial. As we rotate this bond, we move into the boat, come back into the other chair. Where does this move to? It's equatorial now, right? So depending on what ring we're looking at, depends on where our substituent is going to go, okay? So we just learned how to draw these guys, right? So this was axial equatorial. Now we do need to kind of teach you how to draw this ring, which is what I call the left-handed version of the ring, okay? Okay, so how do we draw this guy? So this is what we know now, and I'm going to show you how to draw this guy as opposed to the original one, which is not the same, yes?
And this is called a flip?
This is a ring flip, yes. All this is doing, we're rotating bonds, and not flips, multiple flips. We're rotating bonds, and it's accessing its other chair, okay? Again, this guy is our methyl. So we've just drawn this. We spent a lot of time learning how to draw this. Now we're going to do the other one. Okay, so how do you think the other ring is going to go? What do you think we're going to start with still?
The same but opposite.
Same shallow V, right? So we're going to start with our same shallow V. But now, instead of focusing on the right-hand side, we're going to do the opposite. We're going to go to the left-hand side. So over my left-hand side, I'm going to draw a line down, dot, about 60 degrees that ends before that original bond. I'm then going to draw a line up, dot, 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 dot. That is going to end before this guy. And this, I hate drawing these because I'm always so bad at these. I'm then going to draw another line down, and we have dot, 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 dot. It's going to end down here. It's not going to end down there, but whatever. And then I'm going to connect the dots for my ugly, ugly left-handed chair. Okay, so I'm not proud of this, and I apologize. It looks all right, I guess, but I know. I'm ashamed. So let's get rid of the green because nobody likes green. These are blue, those are black, and this guy is red. Okay? So unfortunately, you guys are going to have to do this. That's why I'm trying to demonstrate how to do it. If we give you a substituent somewhere, we're going to need to see both of the various versions of the chairs. So you can draw this guy now. You also need to be able to draw this guy. But again, as we noted, when this was in the axial position in our right-handed chair, what position does it move into when it flips into the left-handed chair? Equatorial, right? So now what was axial is going to be equatorial.
Everything that was axial now flips to?
Yes. They all switch positions, yes.
And how do I know which corner to put it on or which?
That's up to you. For monosubstituted, you get to always pick, and I always pick the substituent on this far right guy, because that first substituent always goes axial up, and that's usually where I always start. So again, you get the choice of where you want to put your substituent, but I would always recommend you putting it at this far right-hand carbon. Okay, so again, you're going to have to do this, unfortunately, and we're going to talk about why this is going to be important, but I want you to go ahead and try drawing these. So I have two molecules, and I want you to draw both chair conformations for them. So both the right-hand chair and the left-hand chair. I bet there's like an actual name for those, but I don't know them.
Like what?
Right-hand chair and left-hand. I think that's not bad. Okay, so we went over this in class. You guys did this on the board. I'm going to go ahead really briefly and try to, in some sort of nice, pretty fashion, draw both of the chair conformations for the following. So for the first one, this again is a monosubstituted chair, meaning there's only one other group off of our cyclohexane. This ends up being OH. Everything else is just hydrogens. So I'm going to draw the right-hand chair first. I'm going to go to my black ink, and we're going to draw a nice shallow V. Shallow V is super important in getting these correct. We're then going to draw a line down. We're going to draw our line across. We're going to draw a line down, and we're going to connect the dots. All right, so this is our first chair conformation. Again, we get sets of parallel lines, so we'll get red parallel to red, we'll get black parallel to black, and we'll get, let's say, blue parallel to blue. Okay, so then this is my right-hand chair. I always like to put this at carbon 1, and I always like to call this guy carbon 1. And so I always usually, because the axial is super easy to draw, I always like to put that directly up, and we'll say this is our OH group. Okay, so this is conformation 1. This is, again, the right hand, so now this is in equilibrium with the conformation number 2, our other chair, which is the left-hand chair. So again, same thing, shallow V. So now we're going to focus on the left-hand side. This guy's going to, nope, that is not it. This guy's going to come down. We're going to come up. This guy's going to come down, and we're going to connect the dots. And this is what I mean when I say I hate drawing these. So we've got red and red, we've got black and black, and we've got blue and blue. I'll draw, maneuver this, blue and blue. Okay, so again, this guy has now moved from the axial position into the equatorial position. And again, I would demonstrate this on an actual model. You can rotate those bonds, undergo that ring flip, and visualize this. And so again, if this is going to be our carbon 1 right here, then we're going to move our OH into the equatorial. Equatorial for carbon 1 is going to be parallel to black lines right now, right? So it's not the bond directly attached to it. It's the one right after that. So we've got black, so this guy is parallel to that, and it's going to be this OH group. Okay, so this is the 2 chair conformations with that one substituent. Okay, so same exact thing with B. There's no difference between these guys. It's just making you do it more to get more practice. So first step, I'm going to draw my right-hand chair. So we got a shallow V. We're going to come down. Oh, I don't like that. We're going to come across. We're going to come down. We're going to come across. So obviously these get uglier as I go along. So we've got parallel, we've got black parallel, and then we've got blue parallel. Same thing, I'm going to define this as carbon 1, so now it's going to be a methyl group that's attached here in my axial position. We're going to have our little equilibrium sign with our little ring flip, and we're going to draw the other version of the chair. So shallow V. Nope. It's always that one, I think, that really messes me up. Coming down, we've got coming up, we've got coming down, and we're connecting the dots. So red, red, we've got black, black, and then we've got blue, blue. And again, this guy is going to be parallel to black if we're at this position. So if we draw black, black, black. And this is a methyl group, so CH3. All right, that's both versions, both chair conformations for those 2 monosubstituted cyclohexanes. Are energetically stable conformations, right? So in theory, this guy is moving between one chair and the other chair at room temperature. If that were true, right, if that were true that both chairs are energetically equally stable, then what would you expect to be the distribution between chairs that are in this position versus chairs that are in this position?
50-50.
It should be 50-50, right? What we find, though, is that's not the case, right? So when we actually do studies on figuring out who is more prevalent at room temperature, when we have our substituents in the equatorial position versus the axial, the equatorial tends to be preferred. So when this is a methyl group, 95% of the cyclohexane molecules will be in the methyl group in the equatorial position. Okay? So now why is that? Why can we think? So there's a couple reasons. The first one is more of a steric type argument, right? So let's imagine we're here. We've got our methyl group in the axial position, and let's imagine that we've got some big bulky group here, okay? So if we have our group in the axial position here, and there's another group over here that's nice and big and bulky, what are we going to have between them? Some sort of steric interaction, right? So what this is called is 1, 2, 3, so 1, 3 diaxial interactions, okay? Because again, it's not interactions with 2 carbon, it's interactions with 3 carbon. So that's number 1. That's not it, though. No, the real reason why we prefer the equatorial is due to the actual various conformations that this guy takes on in the staggered conformation. So let me try to explain this, okay? All right, so we're in the axial position right now, right? We've got our methyl group. It's pointing directly up. We're in this version of the chair, okay? Now, if I'm looking at the Newman projection for this, and I'm going down this bond, this is one of my substituents on my front carbon. This is one of my substituents on my back carbon. What are these guys relative to each other? They're staggered, right? But are they in the gauche position or are they in the anti-position? This guy and this guy, right? Because I'm looking down this bond. So I've got 2 different guys. I've got this guy. They're staggered. They're not eclipsed, but are they gauche or are they anti with respect to one another? These 2. They're gauche, right? Remember, gauche is when they're directly 60 degrees away, okay? This is axial. They're in the gauche position. When I move and flip this ring, and we're looking down the exact same bond, this bond, here's my substituent, here's my other substituent, now what are they relative to one another? They're anti. So who's going to be more favored stability-wise with respect to being either gauche or anti? Anti, right? And so that's why when we have one substituent that comes off the ring, the equatorial position is energetically favorable because it puts those substituents into anti-position relative to one another, okay? So there's a steric argument. We avoid these 1,3 diaxial interactions, but there's also a conformational argument where we get our groups into the anti-position relative to one another. And again, you can draw the Newman projection for these guys and see again, when this is equatorial, we're anti. When it's in the axial, we're gauche. Okay? Okay, so if I said what is going to be the energetically most favorable or lowest energy conformation for that cycloalkane, what would you tell me? When the OH is in the axial, when the OH is in the gauche?
You mean
No, you meant equatorial.
Equatorial.
Yeah.
Yeah, pardon me. Sorry,
Yeah.
God, words. Okay.
We
So, yeah,
followed.
the type of question that you would be asked would be, here's our cyclohexane, right? There are two different chair conformations. Which one is the energetically most stable conformation?
equatorial?
This guy, because we put our substituent into the equatorial position. Same thing over there. Okay, so for any monosubstituted, meaning one group off the cycloalkane ring, we're always going to put that in equatorial if we want the lowest energy conformation. What if I wanted, no, that's it, because the highest would be a low conformation. We don't. So this is always going to be lowest energy. Which means it's more stable. So that's why we find it there more often than not. 95% of the time we're going to find it in that position because energetically that's the most stable conformation, and we're always trying to get to the most stable situation. Yes?
And now in these two in comparison, so because of this and because of this, these are anti and these are gauche.
It's
right?
the bond that we're looking down here is this bond, right? So if we were trying to imagine this, it would be looking down this bond and relative to this. It's better if I have a model. It's better, it's easier to see it. So if we're looking down this bond, this is our front carbon. We've got the OH sticking up. On this back carbon, this is the group that we're looking at relative to this guy.
Okay.
It's not the hydrogens that are sticking out here, it's this group going out here. Right now, they are gauche, whereas over here, looking down the exact same bond, and now it's turned over here, right? Now we've got these guys anti with respect to one another.
Okay.
And again, a model would be a lot more helpful to see this. It's still the same bond. This is carbon 2, this is carbon 1. This is carbon 2, this is carbon 1. We're still looking at the exact same angle. Now this guy relative to this guy, they're completely apart from one another. I know, it's really hard on the board. And it's really hard to draw the Newman projection from these.
Well, our quiz would be bold.
Are you gonna expect?
I'm not going to expect you to draw a Newman projection,
Okay.
but I do need you to know that putting the substituent in the equatorial position is the energetically most favorable, most stable, lowest energy state. Okay, so we'll stop. We have like 2 more slides talking about what happens if we add on another substituent. How do we know where to put those guys? We'll do this on Wednesday, and then we'll move into Chapter 5. So because of that, your homework will be due on Monday. Chapter 4 homework is due on Monday. Change that in the Canvas site to Monday. I also have your quizzes from last week, so just as a couple of reminders. We had talked about cyclohexane, so ideally we had learned how to draw our chair conformations of cyclohexane. And at the end of last class, we were talking about monosubstituted cyclohexane, right? So this is a cyclohexane ring with one substituent on it, okay? And so we were taking our bond line structure for, let's say, one methyl group on our cyclohexane, and we were converting that to the chair conformation, right? So if we have our bond line structure over here, and I want to convert this to the chair conformation, it's important first to define, let's say, where you want to put that substituent. Okay, so we'll say we're going to put this at the number 1 carbon. So we go ahead and we draw out our chair conformation as best that we can without our stencil, right? And so I always draw the right-hand chair first. And so again, that's starting to look really ugly. And I always like to define the first carbon as this carbon up here, okay? So in my right-hand chair conformation, just to make things easy, I'm going to put that methyl substituent on my number 1 carbon, and I'm going to put it in the axial position. So this guy's going to go in the axial, okay? And so remember, for axial, we're going up and down as we go along the ring, okay? Now, that's one chair conformation. There's another that we're allowed to access, right? At room temperature, these guys are interconverting. And so they interconvert via a ring flip. And again, a ring flip is not just flipping the ring, it's actually moving the bonds so that we get the left-hand chair conformation. And so we can go ahead and draw that. And again, this is only going to get worse at this point. So we've got this guy going down, this guy's going to come up, we're going to go down, and we're going to go down. And so if our methyl group was in the axial, in our right-hand ring, so we're in the axial position in our right-hand ring, we're sticking up. When we rotate this and find the other chair, where has it moved into? It's moved into that equatorial position. And again, that equatorial position is parallel to these guys, but it's on that exact same carbon, right? So that carbon that was pointing up now points down. It's this carbon, and so we're going to be parallel to the things that are away from it directly, okay? Okay, so now we have a methyl group in the axial versus a methyl group in the equatorial. And this is, again, depicting the exact same molecule. We're just interconverting between our various rings, or our various chairs. Now, we got to the end of last class with this monosubstituent thing, and we said, okay, well, when it's in the axial, we have this unfavorable, energetically, gauche interaction between our front carbon in the methyl group and this back carbon and this methyl group going off to the side. Well, instead, we put it in the equatorial position. This group and this group are now anti with respect to one another, right? And so energetically, we said that's more favorable, right? So this was going to be more stable. That means that it is at a lower energy. And we're going to find our chair in this conformation with the substituent in the equatorial position the majority of the time because of that, okay? So more stable, we're at lower energy, and so this is going to predominate when we actually go and look at our chairs, okay? So now, if the equatorial position is lower energy, who is the higher energy chair conformation? The other one, when we put it in the axial position. So if I asked who is the higher energy chair conformation, you would want to put it here. This is going to be higher energy.
Wasn't that one of the questions?
That was one of the questions.
It was one of the questions.
It was one of the questions. In the
Pretty sure got that question wrong.
Yes.
So I'm having trouble with the inside axial. I see the axial, but not the equatorial, how you draw the inside carbons.
The inside carbon.
Inside the chair.
What do you mean?
So obviously the axial will go up.
For this carbon?
No, if we're just talking about the carbons inside
Okay.
the chair.
Okay.
How do I know which side to put in the equatorial?
Yeah.
Does that make sense?
Yeah.
What do you mean?
Here,
I'm
let
not
me
quite
show
sure
you.
what you're saying.
So obviously the axial will go up and this one will go down. But how do I draw the side? Will it go this way or this way?
It's always going to be parallel to the bonds that are not directly attached to it but are adjacent to it, right? So for example, for equatorial, this guy, this position, let me highlight. So this guy, the equatorial, is always going to be adjacent to not the bond that it's directly attached to, so not adjacent. Not these guys, but it's going to be parallel to this guy, right? We get these sets of parallel lines. And so this guy is going to be parallel to these guys, right? So we draw it out.
So those I see, but not the inside.
The
Those are
inside one. So same thing for this guy. So we start at 1, our axial is going to go down directly for these guys, but this guy is going to be again parallel to, now we're going to be at, we'll go red here, these guys. Nope, wrong one. This guy is going to be parallel to these guys, right? And so parallel.
I'm talking about carbon 3 and carbon 6.
Okay, so carbon 3 and carbon 6, this guy's going to go up. This guy's going to be parallel to these guys.
Okay.
So it's always going around. It's always going to be parallel, not to this, but to the next things.
So on the flip ring.
On the flip ring, it's the exact same thing.
Carbon 2.
So now this guy's going to be down. That's our axial. Our axial here is going to be up. This guy's going to be parallel to, we've got this guy and this guy, so this guy. So finding the equatorial always is just going not the bonds that we're attached to, but the bonds that are going to be parallel to the bonds that are directly adjacent.
No.
So then moving here, we go down again. This guy's going to be parallel, not to this, but to this and this. So we're here.
So everything that was like, I guess, like straight over there is gonna be bent over here, kind of like at an angle, because it's gonna be parallel to another one.
So yeah, so everything that was sticking up on the first one, that was axial or was down or was axial was down, is now going to move into the equatorial position. But the way you find the equatorial, where they actually are, is still the exact same thing. This guy's parallel to these guys. This guy's parallel to these guys. Yes.
Can you please show me carbon 6 on the axial?
Carbon 6, which one?
On the axial, the left side.
On the left side.
Yeah,
So
carbon.
this is carbon 1. You want this guy?
Yes.
Okay, so this guy, the axial position goes straight down. The equatorial is going to be directly parallel to this and this.
Okay.
So it's here.
So the inside ones, whatever the outside, the direction the outsides are going, that's the direction it's going to go.
It's whatever the bonds that are directly adjacent to it are going, that are going to be parallel to that, right? So this guy is not going to be parallel to these, it's going to be parallel to these.
Okay.
This guy is not going to be parallel to these, it's going to be parallel to these. And it's the same thing over here. You're going to find where to draw the equatorial the exact same manner. If I said, oh, I want to draw the equatorial position for this guy, I'm not going to be parallel to these, but I'm going to be parallel to these. So it would go out here.
Right.
And then axial is always just up. If we're pointing up, it's down if we're pointing down, regardless.
Thank you.
Does that make sense?
Yeah.
I don't know if I'm answering the
guess,
question.
So what I'm having trouble with is these two in the middle. I see this one goes up, this one goes down, but I didn't know which side. But if I notice that whatever direction this is going, that will do the same. This is going this way, so this will do the same.
Yeah.
Thank you.
Mhm. And again, too, if you want to look at them and have your little model kit out, you can directly see, let's say this is carbon 1, this is carbon 3, where is it? It's right out here, right? The equatorial is right out here, same thing out here, except we're just pointing away from the ring.
Okay.
The model kit helps out, especially with cyclohexane. Okay, so we're going to keep talking about this because we have to talk about dye-substituted rings. Unfortunately, that all is going to be on video. So us pointing at the board, yeah, okay, anyways, doesn't matter. All right, so
Oh, sorry.
big moral of the story, right? So we have two rings that we can freely interconvert between, right? If we have a substituent on there, though, now we're going to influence the fact of one ring being more favored over the other, right? Because again, that substituent is going to want to go into the equatorial position because it's energetically more favorable, energetically more stable. And we can actually calculate the energy's difference between putting it in the axial and putting it in the equatorial. And that's what essentially they're showing you in table 4.8. So they're giving you these actual energy differences depending on the substituent. Okay, so if we had a methyl substituent, that energy difference between axial and equatorial is 7.6. If we get up to a tert-butyl substituent, that increases dramatically, right? So again, for tert-butyl, there's going to be a very large energy difference. It ends up being 22 about kilojoules per mole, putting it in the equatorial preferentially over the axial. Okay, so these don't necessarily matter right now, but they are going to come back into play when we're talking about dye-substituted cyclohexane, cyclohexane. Okay, so now that's monosubstituted. We're going into dye-substituted cyclohexane. Okay. Now, before we do that, we have to mention a couple things, because again, when we're looking at these and we're looking at these energetics and this stability, we always want to compare chair conformations. But again, they're going to be giving you bond line structures, right? So it's your responsibility to take a bond line structure and be able to convert it to the chair conformation, okay? And so we're going to talk about, when we introduce this idea of multiple substituents, we're going to talk about how to do that, okay? Okay, so in bond line structure, we utilize our little wedge and dash to indicate three-dimensionality, right? So what does the wedge mean?
Close to you.
So it's coming out at you, right? So we have our wedge here, meaning it is coming out of the plane of the board. And what does the dash mean? So dash is going to be going away from us or going into the board, okay? Now, as we move through taking this guy and trying to convert it to the chair conformation, what we're going to define for the wedge is we're going to say that the wedge, since it's coming out at us, we're going to define it as going up, okay? So our wedge is going to be in an up position, whereas a dash, since it's going in, we're going to say that it's going to be going into a down position, okay? So if we have something on the dash, we're going to consider that going into the down position. If we have something on the wedge, we're going to consider that up, okay? So now, if we're taking this guy and we're going to convert it to our chair conformation, first thing is drawing the chair, right? So I'm going to start with my right-hand chair. Draw down, draw across, connect the dots, okay? So now, I'm also going to go through and say, all right, I'm going to call this carbon 1, I'm going to call this carbon 2, and on my right-hand chair, I'm going to call this carbon 1, and I'm going to call this guy down here carbon 2. Okay, so we have a carbon 1, and then we have carbon 2. Okay? Now, if we look at carbon 1, we have two options, right? We have an axial position, we have an equatorial position. And if we look at our actual molecule here, right, so again, this is carbon 1, who is up in this position? Is it the axial position or is it the equatorial position?
The axial.
It's the axial, all right? So again, what we mean by up is we're coming above the plane of the actual ring. So right here, for carbon 1, there are two options. We have axial, equatorial. Axial is the up position for carbon 1. So for this guy, for chlorine, we've defined it as up because it's a wedge. So we're going to put that in the axial position because at that guy, wrong one, because at that position, that is what is up, the axial position, okay? If the chlorine is up in the axial position, then what's in the equatorial position? We can go ahead and draw that on too. Just an H, right? So if we want to go ahead and add on the equatorial position here, again, this guy is going to be parallel with, this guy is going to be parallel with this guy and this guy. So then I draw this guy out, and this is going to be my H. Okay, so then that's one. We'll put on our little chlorine onto our axial position. Now as we move to carbon 2, we know that we have a methyl group that's supposed to be going down, right? So again, we have an option. We can put it in the equatorial or the axial. Who is down at carbon 2? It's axial again, right? So because this is the down position, we're going to put our methyl group, because it's going down, in that axial position. So this will be our methyl group. Okay? So then again, if we want to go ahead and draw the equatorial position on, what is the equatorial position at that carbon 2? It's hydrogen again, right? And now it's going to be parallel to this guy and this guy. So we've got a hydrogen coming out here. Okay, and so we'll go ahead and add on that methyl group onto our carbon 2 in the axial position. Okay, so this is what we've defined. Again, we're defining wedges as coming up, and we're defining dashes as going down. Yes?
Is it okay if we put the hydrogen on the other side?
No.
No, it has to be.
Because again, if we look at this, where is the hydrogen?
Oh, yeah.
It's not pointing into the ring, it's directly coming out. Okay. Same thing here, it's not going into the ring, it's directly popping out. Yes?
So if there were both wedges, Then the bottom 2 carbon would be in the equatorial?
So if
Is
they're
it
both, it's
not-
not the carbon, this would be down still, right? The 2 carbon would still be down. The down position for carbon 1 though, if it was a wedge, is the equatorial position, because the up is the axial.
And what about for carbon 2?
Carbon 2, if it was a wedge still, it's still down. For carbon 2, that down position is always the axial.
Okay.
For carbon 1, that up position is always the axial. Okay?
Wait, I'm just saying that if the methyl had a wedge instead, then would it
The
be
methyl
with
does have a
H?
wedge.
What?
The methyl has a wedge.
Well, that was a dash.
Oh, pardon me, so sorry. Okay, yes, sorry. Where it's axial, equatorial, if the methyl had a wedge, then the up position of carbon 2 is not the axial because it's pointing down. The up position is the equatorial,
Also, then where the hydrogen is at.
where the hydrogen is at, yeah. So it goes around, again, axial helps you kind of see what's up and what's down. If you need this guy to be up, this position is down, so it has to go into the equatorial.
So you kind of choose whatever is kind of the most going down. If it's going down, go with
Yeah.
whatever's going down.
So again, if you could look around these, it's this idea of what's above the plane. At this position, this equatorial is technically above the plane. It's not as much pointing up, but it is slightly pointing up. Okay, so then that's one ring, right? So we've got our carbon 1, we've got our carbon 2, we've got up, we've got down. What's going to happen now, though? This is not the only ring conformation. All right, so now we're going to ring flip. So we've got nice little equilibrium. We've got a ring flip. And again, we're going to try to draw our left-hand ring, left-hand chair conformation. I'm going to get this guy. I'm going to get this guy, and this guy. Okay? So again, if we take our ring and we flip it, right? Now, carbon 1 is here. We've got carbon 1. We'll go ahead and highlight that. And carbon 2 has now moved to here. And we'll highlight that. So this guy is carbon 2. And we can write that 1 and 2. Okay, so we were in the axial for carbon 1. We're still up. Where has it moved to now, though?
Equatorial.
It's moved to the equatorial position, right? This is still for carbon 1 on this left-hand ring. This is still the up position because the down is the axial now, okay? So this guy has moved to the equatorial, and we can go ahead and draw that in right here. So this is our chlorine. Now, same thing as we move along to carbon 2. This is carbon 1. Where has the methyl group moved to? To the equatorial as well, right? So again, we were here. It was down. It was in that axial position when we flipped the ring. Now this guy is up. This is still down. It's just the equatorial position that's down now in this left-hand ring structure, okay? So for this guy, we'll go ahead, we'll find our parallel lines, and then we'll draw the methyl group out here. I hate blue. I think it's the light. You know, it looks really good on here, but it's just a projector, okay? Okay, so that's the big thing, and that's what I'm trying to stress here, is that up and down are not, oh, it's always axial, it's always equatorial. It depends on the position, okay? So if you draw the right-hand ring, the axial for carbon 1 is always up. The equatorial is the down, right? For carbon 2, the axial is down, the equatorial is up, okay? Okay, so now if we thought about, well, we'll come back to this because we're going to do a problem, but we're also going to be considering the energetics between the two, right? Because again, one of these is going to be favored, and we're going to talk about that once we get a little practice drawing these chair conformations. Okay, so now let's take a little time. Got a couple of di-substituted cyclohexanes. And I want you to draw the two chair conformations for both of these molecules, right? So again, you can define whatever you want as carbon 1. That's the big thing to note. For this one, I would say this is carbon 1, 2, 3. For this one, I would say this is carbon 1, this is carbon 2, and so on, okay? Yes?
For B, is CH just pointing this is what it is, or
So
there's
this
an
is
attachment?
This is an ethyl group. right? But it's saying that this is going, an ethyl group going into the board. So this is an ethyl that's going in. Okay, so go ahead and give this a shot. For both A and B, you're going to draw 2 different conformations, depending. So you should overall get 4 different chair structures out of this. Okay, so give it a shot, push pause, and then come back, and I will draw out the answer. Okay, so I'm going to start with A. So we'll write over here A. And so in A, again, I said you guys can define the carbons however you want. I've started with this carbon being carbon 1. That's going to make the bromine carbon, carbon 3. Okay, so now we talked about in that previous slide how, okay, anything on the wedge, which is coming out at us, we're going to define as being in the up position at whatever carbon we're dealing with on our cyclohexane ring. And then anything on the dash, which is going into the board, we're going to define that as being in the down position at whatever carbon we're talking about. Okay, so for A, the first thing I'm going to draw is, again, what I've been referring to as this right-hand ring, which is the right-hand carbon being the uppermost carbon. So again, if I start with a shallow V, and I draw this guy down, and this guy, and then we'll get this guy. It's not super pretty, but we're going to go with it. I can pick whichever carbon on this ring that I want to be carbon 1, right? So that is up to me entirely. I preferentially will pick specifically this carbon because it's always there. It's always the easiest one to find, right? So if I did that, hold on, I want to finish making this a little bit prettier. Because, yeah. Okay, so if I did that, if I said this guy is going to be my carbon 1, then I usually also will move in like a clockwise direction and how I number the rest of them. So if this guy is carbon 1, then I would say that this is carbon 2. This guy specifically is carbon 2, and then this one is carbon 3. But if you had wanted to go the other way and say that this was 2, you could do that, and then this would be 3. Both of those would be correct answers, right? I just tend to go in the more clockwise direction when I number these things, okay? All right, so then starting at carbon 1, we know we have a methyl substituent, and that methyl substituent is on the wedge, so it's going to be in the up position at whatever carbon we're at. So if this guy's carbon 1, the up position is the axial position of this carbon, right? At this carbon, the axial comes up above the plane of the ring. And the equatorial, so the equatorial, which is going to be parallel to this guy, is actually going to be the down position here, okay? So if axial at this carbon is up, then we're going to go ahead and draw our up methyl. And then the other thing that's implied, which is on the down, we can go ahead and draw that here, is that hydrogen, right? So we can go ahead and draw in that hydrogen, which is in the equatorial at this position, which is down for this carbon, okay? All right, so then as we move around the ring, so if I go to carbon 2, I know that at carbon 2, the equatorial is down, right? It points down below, oh, not equatorial, the axial position is down now. It goes up, down, and now the equatorial position, which is parallel to this guy, is actually the up position. Again, at carbon 2, we're not super concerned. These are both just hydrogens. Now as I move to carbon 3, so axial went specifically up and then down. Now again, we're at an up position at carbon 3. So at carbon 3, the axial is up, and that's where we want the bromine. Bromine is also going to be up. It's on that wedge. So this guy would be here. And then in the down position here is the equatorial. Equatorial is going to be parallel to this guy, so it's going to come out like this. Now, the things that you really would have had to have drawn to actually show me this conformation, you don't have to draw any of these hydrogens, right? So this is just kind of keeping track of where we were along the ring. And you don't have to draw these hydrogens either. Again, it's just keeping track of where we are around the ring, okay? But if you wanted to draw them, you could. It's up to you. All right, so now, if that is our right-hand ring, then we're also going to go ahead and draw the left-hand ring. So this is going to undergo a ring flip because, again, we want both conformations. So then the first step in this is drawing the left hand, the other version of the ring. So again, we'll start with our shallow V. Now we'll come down from the left carbon and we'll come up. This guy's going to come down, and then this guy's going to come down. We'll connect the dots. So again, like I say, this gets really ugly when I start to draw these left-hand carbons, or left-hand rings. Okay, so again, this is where a model kit will be very helpful. If you've defined this guy as carbon 1 over on the right hand, that becomes this carbon in the left-hand ring. Okay, so that guy is carbon 1. So we can say this guy's carbon 1. Therefore, you'll follow this guy to carbon 2, and now this guy is carbon 3. Okay, so again, it doesn't matter which version of the ring you're drawing, right? The methyl in both left and right is still going to be up. The bromine in both left and right is still going to be up, right? They're still going to be on those wedges. The only thing that changes is what position is actually up at each of the carbons, right? So on the right-hand side, the axial position was up. Now that we've undergone a ring flip, it's actually going to be the equatorial position, which is up. Because now this carbon, if we draw the axial is now down. That methyl is still in the up position. So the methyl now is going to be in the equatorial position, which again is parallel to this guy. So we can draw this guy out. So this is CH3. That hydrogen is in the axial. This is in the equatorial. And again, it's hard to see this whenever we're drawing these rings on the board or on the page. But this equatorial position is up. If you actually had a model, you would see that this guy in this position is above the plane of the ring. Okay. So now, same thing as we go around. If this is carbon 2, we don't care about it. We come to carbon 3. Carbon 3, if this guy has the axial as the down, then the equatorial is going to be the up. The bromine is in the up, so we also have to draw it there. Equatorial here is not parallel to this or this, but instead it's parallel to this guy. So if I draw this guy out, we've got bromine in this position. Okay, so these are the two different conformations. Again, you don't have to include the hydrogens, but it's just helpful for me to keep track of where we're at. And in this one, we've got both of our substituents in the up position in this version of the ring, which are both in the equatorial position. Okay, so then we move on to B. So B, we've got carbon 1, carbon 2. This guy is up, but now our ethyl is going to be in the down position. So again, I'm going to go ahead and draw my right-hand ring first. Draw down, 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 down. I'm going to define this guy as carbon 1. And there's a methyl here at carbon 1. That methyl is up. And we know at this position, in this ring, up is the axial position. So I can easily draw the axial and say that this is a methyl group. Again, I like to continue to number this way, so this is what I'm going to call carbon 2. At carbon 2, in our two-dimensional structure here, we've got an ethyl group going down. And so our carbon 2 is this guy, and specifically at this carbon, the down position is also axial, because remember, axial goes up, and then it goes down, and then it goes up as we move around. So down here is the ethyl group, also in the axial. So this was axial up. Now we have axial down. And you can represent this as just an ET if you wanted to. You could also draw out CH2, CH3 if you wanted to, or you could really just draw out the bond line version of the structure. But again, for one of these versions, both of these guys need to be in the axial position. So this is our right. This is our right. We're going to undergo a ring flip. And we're going to draw the left-hand version of our ring. We're going to attempt to draw it. Okay, yep, upset with that. So we've got this guy, this guy. This guy's going to come down. This guy's going to come across. Nope, that's not what I wanted. I want an eraser. Eraser. This guy, a little bit more, down, a little bit more, and then down. Okay, so, God, that's really ugly. I really hate drawing those. Okay, anyways, we've got our carbon 1, which becomes this guy in this version of the ring, and then we've got our carbon 2, which becomes this guy in this version of the ring. Okay, so now, at our new carbon 1, at this guy, our substituent is still going to be in the up position. The up position now is not the axial, because axial points down for this guy. The up position is instead equatorial, which points out, it's parallel to these guys, which points out. So this guy is our methyl. Then we move to carbon 2. Carbon 2, we need that ethyl group in the down position of this carbon. So this was a hydrogen. So up for this carbon is the axial position. Down is going to be the equatorial position. That's going to be parallel to this guy. So we can draw this guy as an ethyl out. So again, the second version of this is essentially, let me erase these hydrogens so I'm not confused. The other conformation here has our methyl group in the equatorial position, which is up at carbon 1. And then it has our ethyl group in the equatorial position, which is down at carbon 2. Okay, so hopefully you guys got that. Monosubstituted cyclohexane. Now we're going to talk about energetics and how to know who is the highest energy chair conformation, who is the lowest energy chair conformation with multiple substituents on it. Okay, so let's say, for example, that we had our little di-substituted cyclohexane. Yes.
You might have already mentioned this, but for ethyl groups, you don't draw 2 lines in the chair. It's always 1 with ethyl.
You can draw, if you wanted to draw this out, you could draw this and this. That's fine.
Okay.
It's preference, as long as it's correct.
Makes sense.
Yeah. Okay, so same thing. We've got a di-substituted cyclohexane. Okay, when I go in here, I'm going to go through and say, okay, this is going to be my carbon 1, this is going to be my carbon 2, this is going to be my carbon 3. Carbon 1, we have an ethyl group on the wedge, right? So we're going to define that as the up position. So this is up. Carbon 3, we've got a methyl group on the dash. So we're going to define that as the down position at that carbon. Okay, so we go ahead and we draw our right-hand chair. We're going to say that this guy is carbon 1. And at that position, on our chair conformation, who is the up position? Is it axial or is it equatorial?
Axial.
This position, carbon 1 on our first chair, on our right-hand chair, who is the up position? Is it axial or is it equatorial?
Axial.
It's axial. Okay, so we go ahead, we put our ethyl group in the axial position. We move over to carbon 2. At carbon 3, we need a methyl group that's in the down position. Okay, now, the axial position at carbon 3 is doing what? It's pointing up, right? So the axial position, which is a hydrogen, is pointing up. That tells us that if the down position has to be in the equatorial position, okay? So that means that, okay, our methyl group, since it has to go down, axial is pointing up, then it has to be in the equatorial position, okay? So we do that. We do that for our first chair. That's our first chair conformation. Now, we're going to have to do a ring flip, right? So in our ring flip, we're going to draw our left-hand chair. Again, this is still carbon 1. This is carbon 2. This is carbon 3, as we've defined it. Now, at carbon 1, the axial position is down, right? So if the axial position is down, but ethyl is still up, it has to go into the equatorial position, and that's fine because we're flipping the ring anyways. And then at carbon 2, that methyl group has to be down, and now the axial is down at carbon 3. Okay, so we flip it, and we've got this guy. Okay? So now the question is, who is the lowest energy chair conformation? For monosubstituted, where did we want to put our substituent to be lowest energy?
Pointing down.
We needed to put it in the equatorial position, right? Because that was going to be anti, okay? So in the first chair conformation, do we have one of our substituents in the chair? No. My God. Do we have one of our substituents in the equatorial position?
In the first
Yes.
In the first chair conformation, yes. Yes, so number 1, we do have one of our groups in the equatorial position that ends up being the methyl group. So we have methyl, equatorial. And then we have ethyl, unfortunately, where? In the axial position, okay? So then in number 2, our other version of the chair, do we have anyone in the equatorial position?
Mhm.
Yes, ethyl, right? So we have ethyl now in the equatorial, right? We have methyl, though, where? Axial. So again, we want our substituents in the equatorial position. That's going to be the lowest energy chair conformation. Unfortunately, both chair conformations has one in the axial, one in the equatorial. Who do you think is going to determine who wins this? The biggest group, right? So this goes back to the energetics, right? As that substituent got bigger, that energy difference between the two got larger, right? So when we compared the methyl to the tert-butyl had a large energy difference, meaning that it was always going to favor the putting the tert-butyl group into the equatorial position. So who's bigger, methyl or ethyl? Ethyl. Okay, so because of that, we want to put ethyl into the equatorial position. Which chair conformation does that? Number 2. Okay, so because this is bigger overall compared to the methyl group, right? We want to put it in the equatorial position for the lowest energy state. So this is going to be our lowest energy chair conformation. And so the majority of the time, if we looked at the distribution of these guys at equilibrium, we would find this molecule in this chair conformation because, again, it puts the ethyl group into the equatorial position. This one, which has the methyl in the equatorial, the ethyl in the axial, is going to be the higher energy chair conformation. Just blurs off into the higher energy chair conformation. So number 2 is going to be favored. It's going to be more stable at equilibrium. Yes.
Higher energy, less stable.
Higher energy is less stable. Low energy is more stable. We're always tending towards lowest potential energy or lowest energy state.
Okay, so favorable, lowest energy.
Lowest energy is most favorable, most stable. Okay, so with that in mind, I would also refer you back to that table that I showed you with the energy differences, because sometimes there's going to be a competition between a couple. So the last little bit that we have in class, I want you to do some of these, and then we'll go over the actual solutions. So I have 2 molecules here, and I want to know who is the lowest energy chair conformation for both of them. So this incorporates our up-down, right? It also incorporates determining who's more energetically stable, who has lowest energy. And again, we're always wanting to put the biggest group in the equatorial position. So start by drawing the chairs for both of these. Then look at them. And then try to figure out who's lowest energy. Okay, so again, I would have paused the video, try to answer these, and then watch the solutions, which I'm now going to go over. I'm going to start with A. Okay, so in A, again, I'm going to define this guy, my top carbon, as my carbon 1. And then I'm going to define this guy as carbon 2. And we're here. And so now at carbon 1, we've got a methyl group on the wedge. So this is going to be at the up position on our cyclohexane ring. And then we've got this guy, if you'll see, is a nice Y. It's a 1, 2, 3 Y. So this is an isopropyl group. And I'm going to abbreviate just isoprop. Okay, so this guy is also on the dash here. So this, whatever axial versus equatorial, the dash, this is going to be in the down position of whatever carbon it's on. All right, so now we're going to look at the two different conformations to figure out which one is the lowest energy. I'm going to draw the right hand ring first. So right hand ring, I'm going to define this guy as my carbon 1. And again, I'm going to move in this clockwise fashion. I'm going to define this guy as my carbon 2. So we have carbon 1. And then we have carbon 2, okay? All right, so carbon 1, we have a methyl group in the up position. So if we're at this carbon specifically, the up position is that axial position. So we can draw this guy as a methyl. I'm going to go ahead and abbreviate this methyl. So we have a methyl at the 1 position, which is up. And then as we move to the 2 position, our next substituent is an isopropyl group, and this is going to be in the down position. So at this carbon specifically, the down position is the axial position. So we have, I hate it when it does that. So we have down and isoprop. Okay, so on this right-hand version, we have axial as the up position, and then we also have axial as the down position. On carbon 2, we're going to have this undergo a ring flip. So now we'll draw the left-hand ring. I just don't know why that gets so bad. I think it's this one. Up, down, and then we'll just erase a little bit from this guy and connect the dots. Okay, that looks a little bit better. So make sure to connect the dots. Okay, so now, again, we had this guy as our carbon 1 over here. That's going to become this guy as our carbon 1 here. So go ahead, say this is carbon 1, this is carbon 2. And I just want to kind of draw this in a little bit better. Okay, so now if the methyl was in the axial on carbon 1 in the right hand ring, then it's going to move into the equatorial on carbon 1. That's going to be the up position now. So this guy is our methyl. It's equatorial in this conformation, and again, this is still the up position. And we'll go to carbon 2. At carbon 2, we've got an isopropyl. It's supposed to be down. So the up position here is axial, the down is equatorial. So it's going to be parallel to this guy. So it's going to come out here. And again, this thing is going to be an isopropyl group. So this is also equatorial, but now it is down. Okay, so I'm going to go ahead and erase this thing I drew here because this is only going to confuse people. So we have two versions here, right? We have both of our substituents in the axial position versus both of our substituents being the equatorial position. I'm looking for the lowest energy conformation or configuration. That is going to be this guy where both of my substituents are in the equatorial, because again, equatorial energetically is more favorable. Moving them into the axial position is going to cost energy, so this guy is going to be my lowest energy conformation, and it's going to predominate the overall makeup of my cyclohexane molecules at room temperature. Okay, so that's number one. Number two, we get a little bit more complex, so we're going to have to think about this a little bit more. So in B, we've got, we'll say, carbon 1, carbon 2, carbon 3. So we've got 1, 2, 3. At carbon 1, we have a methyl in the down position. Carbon 2, we have a chlorine in the down position. So again, we have dash, dash. And then at carbon 3, we have a chlorine in the wedge, which is up.
So anytime it's on the dash, it's always going to be down. Anytime it's on the wedge, it's going to be up. Okay, so I'm going to go ahead and draw my right-hand ring first. Okay, and I'm going to do the same thing that I've done before. We're going to have 1, 2, 3. So we have 1, 2, and we have 3 over here. I'm going to start at 1. I've got a methyl group in the down position. So at carbon 1 here, the up position is axial. The down position is equatorial. So I'm going to get rid of that axial. I'm going to draw the down position, which again is going to be parallel to this guy. So this guy is a methyl group, and it's in the equatorial position. At carbon 2, we have a chlorine in the down position. The down position here is the axial position, so we can just draw this straight down. So this guy's a chlorine. And then we have at carbon 3 in the up position of chlorine, this carbon is carbon 3. The up position here is the axial as well, so we'll draw chlorine up. So we have an equatorial methyl, we have an axial chlorine, and we have another axial chlorine. We're going to undergo a ring flip here. We're going to draw the left-hand ring. Okay. God, it makes me mad. Okay, so same thing, right? We had carbon 1, 2, 3. Now it's going to be carbon 1, 2, 3. We have a methyl group at carbon 1 in the down position. At this carbon now, the down position is axial, so we can draw this down as a methyl group. So we have an axial methyl group. Now we have at the carbon 2 position, we have a down chlorine. Up here is axial, so down is equatorial. It's going to be parallel to this guy. So we have a chlorine in the equatorial position. And then at carbon 3, we had an up chlorine. So the down position here is axial, the up is equatorial. Again, it's going to be parallel to this guy. So we have an equatorial position coming out here. So then I'm going to erase these extra axials that I've drawn so we don't get confused. And I'll go ahead and fill this in with chlorine. So this is also equatorial. Okay. Now, if we're looking at these two different conformations, here we had an axial chlorine. We had an axial chlorine. We had an equatorial methyl. Here we had an equatorial chlorine, and an axial methyl. Right? So you would think, okay, well, we'll say this guy is number 1, this guy is number 2. In number 1, we had 2 things in the axial position and 1 in the equatorial. Here we had 2 things in the equatorial, only 1 in the axial, right? And so again, if we're looking for lowest energy conformation, we want things to be in the equatorial. So you would say, oh, well, you have 2 things in the equatorial, so this must be lowest energy, right? And you would say, okay, well, that's great. But you actually have to look at the numbers here, right? So on that previous slide, I had given you some numbers for having, or the energetic penalty or the energy associated with having various types of substituents in that axial position. And so here we had found that for chlorine, if you look back on that slide, that ends up being about 2 kilojoules per mole. Same thing for this chlorine. Any chlorine is 2 kilojoules per mole for putting it in the axial position. So overall, the energy penalty here is 4 kilojoules per mole. Whereas if we look at the axial methyl group, that ends up being actually 7.6 kilojoules per mole, right? So total energy penalty of putting that methyl group into the axial position is 7 kilojoules per mole, right? Versus only 4 for having 2 axial chlorines. So because of that, because this is lowest, this is the actual lowest energy conformation. Even though you have 2 things in the axial position, those 2 things don't cost as much energy as having this one guy, right? So
With respect to these numbers, I don't expect you to memorize them. Please do not even attempt to memorize them. That's silly. It would either be obvious, like this one, where you literally have two things in the equatorial versus two things in the axial, or I would give you the numbers myself in some sort of exam or on the homework, and you would be able to calculate who is actually the lowest energy conformation, right? But this guy, number 1, is lowest energy, even though there are two things in the axial position, because those two things don't cost as much energy as having this one thing in the axial position does. Okay, so that is it with respect to cycloalkanes. I don't know how long this is going to go, so when I upload this, we'll see how long it takes. And then I'll maneuver my next lecture accordingly. So in the next chapter, we're going to deal with stereoisomerism, and I'll introduce that whenever we get to that on Thursday. Okay, so yay, good luck. Email me if you have questions, and okay, bye.